In this video, we're going to look at simplifying radical expressions. And radical expressions are like this expression here, square root of x. And what a radical expression is you have what we call a radicand, which is a value that's underneath a radical symbol. And the radical symbol indicates the type of root that you have. And we have multiple types of roots. There's square root, cube root, fifth root, fourth root, sixth root, seventh root. You can go on and on and on and on. So the radical sign indicates that you're taking some kind of root. And normally there will be a small number right here, an index, in front of this radical sign that actually tells you what root you're taking. In square roots, you commonly don't write the 2 there, indicating that's the root that you're taking. So we have the vocabulary. We have a radicand, which is the value that's under your radical sign. And we have the radical symbol, which indicates what type of root you're going to take. And then we're looking at square roots in this particular lesson, so we're looking at perfect squares. And what a perfect square is, it's an integer that is the square of another integer. So your perfect squares, I gave you some examples here. We listed them. 1, 9, 16, 25, 36, 49, 64, 81, 100. Those are the most common ones you're going to see. That's the square of the numbers 1 all the way up through 10. So that's what a perfect square is. So we're going to look at these examples here, 1, 2, 3, and 4, and we're going to try to simplify these as much as we can. Now, not all of these radicands and not all of these roots that we're being asked to take are perfect squares. So we have to find some way to simplify them. And this method we're going to use to simplify can not only tell you the simplest form of this radical, but it'll also tell you ultimately, if you do it properly, whether or not it is in fact a perfect square. So let's look at number 1. Now number 1, based on what we see here, we shouldn't have to do any work on number 1. We know that number 1 is a perfect square, and that is 5. So the answer to number 1 is 5. Now, why is the answer 5? 25 is what we consider a perfect square, because if we square the integer 5, we get the integer 25. And that's what a square root is. What is it that we squared to get this radicand? What did we square to get 25? And in this case, it's 5. So those are the ones that are the easiest to solve. It's a perfect square. We know right away the square root is going to be 5 for this one in particular. So let's look at number 2. If you look at number 2, you'll notice that 75 is definitely not a perfect square. So the question is, how can we simplify this? Well, what I'm going to do is I'm going to use something called a factor tree. So I'm going to take my 75, and I'm going to set it up over here, and I'm going to try to factor this out into all of its prime factors. I want to factor until there are no factors left other than prime numbers. So let's look at 25. The first thing we're going to do, we don't want to do 75 and 1. That doesn't get us anywhere. We already have 75 and 1. We want to break this down further. So I'm going to go 25 and 3. Observing the 2 factors that I have, I realize that 3 is prime, so I'm going to circle that. That ends that particular branch of our tree. I do have 25 over here, so I'm going to take the 25 and I'm going to factor that out, and that is 5 times 5. And again, 5 and 5 are prime, so that ends those branches. So I'm done with my prime factorization. So basically what this means is that 75 is the same thing as if I wrote the product of 5, 5, and 3. So I'm going to rewrite 75, and I'm going to order the factors from smallest to largest. You don't have to, but it makes it easier for you to match up for the pairs that we're going to look for. 3 times 5 times 5. Once I've done this, I need to look and see if I have any pairs. And I do. I have 1 pair of 5s. Now, what does that mean? That pair of 5s means that I can bring the 5 outside, because what is 5 times 5? It's 25. What's the square root of 25? It's 5. So for every pair, 1 comes out, and then the 3 doesn't have any buddies. It's by itself, so it just stays underneath, and that is your simplified answer, 5 times the square root of 3. There is an alternative way to do this using the factor tree, and it's going to be your preference as to what's more comfortable for you. And I'll go ahead and illustrate that over here. Let's start with 75 again, and we're going to do our factor tree the same way, 25 and 3. But some people are good enough to notice that 25 is a perfect square, so I'm going to box it in with a square. Knowing that this is a perfect square, we know that the square root of this value is going to be outside of the radical, because that means that 75 can be written as the same thing as the square root of 25 times 3. And we know what the square root of 25 is. It's 5. And what's left underneath without a buddy? The 3. Same answer, 2 different approaches using your factor tree. So it's your preference. It's not going to bother me which one you choose. Sometimes when we factor prime factorization, we don't always put ourselves in a situation where we have a perfect square. So you would definitely need to know how to do this. But if you're good enough at finding those perfect squares, this would work too. So let's move on and let's look at the next one, which is the square root of 30. I'm going to do the same thing. 30 is not a perfect square, so I'm going to actually take it and do my factor tree. The easiest thing to do for 30 is 3 times 10. If you want, you can do 2 times 15. If you want, you can do 6 times 5. Not everybody's factor tree is going to start off the same way. And that's the nice thing about a factor tree is once all of your branches end and you've gotten to all of your prime numbers, everybody's prime numbers are the same regardless of the initial factors they choose. So I'm going to circle my prime number 3. And just to remind you, a prime number is a number whose factors are only that number and 1. So 3 is a prime number because the only factors of 3 are 3 and 1. So let's look at 10. 10's not prime. I can actually break that down a little bit more. So I have 2 times 5. Now both of these guys are primes. So now I'm done. All of my branches have been completed. I've gotten to prime numbers. So let's rewrite this. Just as we did up here with the 75, 3 times 5 times 5, I'm going to rewrite the square root of 30 as the square root of 2 times 3 times 5. So I've taken all of my prime factors. But what do we notice in this particular situation? There are no pairs. No pairs mean that there's no perfect squares. Notice up here we had a pair of 5s, 5 squared. That gave us 5 because that was a square. We could bring it out. I don't have any pairs here. So what does that mean? Well, that means that the square root of 30 that you had is already in its simplest form. We cannot simplify this any further because there are no perfect squares within those factors. That's as far as we can go. And so you'll have some of these where you can break them down into all the prime factors, but there's no pairings and no perfect squares in the factors. So we're already in the simplest form. All right, so I'm going to do one more example. And that's going to be the square root of 108. And the square root of 108, a little bit bigger number. So we're going to have a little bit bigger factor tree. Now I will tell you a little trick. 108 is a big number, but there's a little trick that you can use when you're trying to factor larger numbers. And especially when you're doing the factor trees and simplifying, it's kind of nice because you can use the number 9, and 9 is a perfect square. So if you want to find out if a number is divisible by 3 or by 9, any number, 1 digit, 2 digit, 3 digit, 4 digit, 5 digit, 1 digit really wouldn't make sense, but 2 digits, 3 digits, and so on, you add the digits together. So in this case, I have 1 plus 0 plus 8. That adds up to 9. That means that this number can be evenly divided by 9. That works for any set, any number. If the addition of all of the digits in that number comes out to 9 or a multiple of 9. For example, if we had 189, this is also divisible by 9 because 1 plus 8 plus 9 is 18. 18 is a factor of 9. 9 goes into 18, so it's a multiple of 9, so this can be divided by 9. So just keep that in mind. That also works for 3. If the digits added together are a multiple of 3, that means we can divide the number by 3. So I know this can be divided by 9. And so if I use my calculator, I do 108 divided by 9, and I get 9 times 12. Okay, so I'm going to do this both ways again, just like I did with 75. So let's do this the longer way first. Neither of these numbers is prime, so let's continue our factor tree. 9 is 3 times 3. Those are both prime, so those branches of my tree are complete. Now let's go to 12. 12, I'm going to use 2 times 6. Could you use 3 times 4? Sure, whichever one you want. We will all end up at the same spot. The 2 is prime, but the 6 is not prime. So I've got to continue on, and the 6 is 2 times 3. So now I've completed the prime factorization. There's nowhere else to go. All of these factors are prime. So I'm going to rewrite the square root of 108, and again, go in numerical order so that you can see your pairs. If you try to go randomly, it's harder to spot the pairs, especially when you have a lot of factors. So I have 2 2s and 3 3s. So like we talked about before, once you have this, you look for pairs. I've got a pair of 2s and I've got a pair of 3s. And remember, the rule is for each pair, 1 comes out. So a 2 is going to come out, a 3 is going to come out, and this is all multiplication. So whatever you bring out is multiplied together. So I brought out a 2 and a 3. Those are going to be multiplied. And then I have a 3 without a buddy underneath. It's a single. So my last step is just going to be to combine all of my terms. So 2 times 3 is 6. So my answer is 6 times the square root of 3. So let's look at if we would have used the perfect square model. I'm going to go back and I'm going to refactor 108. And I'm going to do 9 times 12 this time. And let's use what we used up here. Do you see a perfect square here? Yes, 9 is a perfect square, so I'm going to box that in. Now let's move on to 12. 12 is 4 times 3, or you could do 2 times 6, whichever. And guess what? I've got another perfect square here. And then the 3 is prime. So now I'm going to use the perfect square principle to get the same answer. So this is the same thing as writing the square root of 9 times the square root of 4 times the square root of 3. And we know that the square root of 9 is 3, so I can bring that out. We know that the square root of 4 is 2, so I can bring that out. And the 3 stays underneath. So I multiply 3 times 2, and I get 6 times the square root of 3. And that is how you simplify using the square roots. It's up to you which one you want to use. The nice thing about solving these and simplifying these is that you can take 2 different routes and you should end up in the same place. It's your comfort zone and your comfort level on the calculations and what process you prefer. So that is simplifying radical expressions. And we're going to use this when we get into our next topic, which is radical functions, which is cube roots, square roots, fourth roots, etc.